Hello, welcome to Fundamentals of Acoustics. Today is the 5th day of this week, and in the last 4 days we had been discussing the concept of power and power flow per unit area as it applies to, the first one was power as it applied to electrical networks, and power flow per unit area as applicable to acoustical systems. What we plan to do going forward is we will shift gears and we will go back to our one dimensional wave propagation equation, but now we will start discussing wave propagation in context of spherical waves. So, in our earlier discussion of one dimensional waves was specific to planar waves, which you can analyze using a Cartesian frame of reference, but in general a lot of sound sources do not propagate wave just in one single direction, rather the sound gets spread in all directions. For instance, you may have a bird tweeting on top of a tree, and that sound, it just does not go in one particular direction, but it spreads in all the directions. Now, in this context, I would like to say that as we start doing this, we will initially assume that there is a point source of sound. So, there is one particular point which is emitting sound, and it is directionally neutral. So, it emits sound in all the directions, it is omnidirectional, and the intensity of sound as observed by a microphone or a person, it does not change with respect to direction. So, those are the type of point sources we are going to consider. So, we will be considering omnidirectional point sources. Point sources of sound. So, you have point and let us say the sound source is located at the center of a sphere. So, if you measure sound on the surface of sphere, then the intensity or the pressure sound pressure level which you measure will be same. So, this is an omnidirectional sound source. So, it is omnidirectional because it is spreading sound in all the directions. This particular sound source, which is spherically symmetric, that is, if you have the source at the center and if the on a sphere the amount of sound which you perceive or which you measure is same, then this type of a sound source is called spherically symmetric sound source. So, omnidirectional sound sources may or may not be spherically symmetric, but spherically symmetric means that the source is located in the center and at all the points on the sphere the sound which is being perceived is the same. Now, that does not mean that if you make the sphere larger or smaller, the sound level may be the same, but for a sphere, if the source is located at the center, that for a particular sphere the intensity of the sound is same. You go to a different sphere, it is same on that sphere, but it may not be same compared to a sphere with a different radius. So, this is what we are going to discuss. Now, what is our aim? Our aim is that if there is a sound source, let us say S, and it is spherically symmetric, then what we are interested in knowing is that suppose there is a person at point P and at a distance r away from the sound source, then what we are interested in trying to figure out is what is the pressure at point P which is distance r away and at a given time. So, that is what our aim is. Our aim is to figure out how does pressure as I move away from a spherically symmetric sound source which is a point source, how does pressure change. So, in this context we will make some assumptions. So, what are the assumptions? The first assumption we are going to make is that it is a point source second is spherically symmetric, it emits spherically symmetric wavefront. The third thing we know assume is that whenever we are going to do these measurements, there are no reflecting surfaces. There are no reflecting surfaces. So, what does that mean, no reflecting surfaces? It means that source may be located somewhere in the sky and there is no object in the vicinity that sound comes, hits it and it gets reflected. So, in the case of a Cartesian frame of reference, we had also accounted for reflections. So, there was a forward travelling wavefront and a reflected wavefront, but here at least for starters we will not worry about reflections and then later we will accommodate reflections, but for starting purposes we will not discuss reflections. So, that is the background and these are the assumptions. So, with these assumptions we will work on the solution or of this problem, that is how is pressure changing as I go away from the source. Now, for one dimensional Cartesian system, we had developed a wave equation, right, and what did that wave equation say? It said that partial of pressure, second derivative of pressure with respect to time is equal to c square, where c is the velocity of sound, times second derivative of pressure with respect to x. So, here we had assumed that p is a function of x and t. Now, if this, now in our case, so here the problem is not Cartesian in nature, right. So, sound is travelling in all directions. So, here it is not a planar wave. So, in a Cartesian frame sound is travelling like this and there are planes. So, if at a given point of time if you take planar cross section, the pressures across the plane are same, but in this case the sound is not travelling like this, but the sound is travelling in all directions, So, here we will have, instead of planar wavefronts, here we will have spherical wavefronts. So, these are the spherical wavefronts which have been drawn here, and on a spherical wavefront at pressure is going to be the same. And if so, let us look at a spherical system for a spherical coordinate system. So, for a spherical coordinate system, so in a Cartesian system we have x, y and z coordinates, and in this case for 1D Cartesian system we had assumed that because the wave is in one dimension only, propagating only in one direction. So, any partial derivative with respect to y and with respect to z, we had assumed that they were 0. Now, if the wavefront is spherically symmetric, now in a spherical coordinate system we have 3 coordinates, one is r, the other one is phi and the third one is theta, right. So, for a spherical coordinate system, if the wave is spherically symmetric, then we can say that any partial derivative of any entity with respect to theta is equal to 0, and so is partial derivative of any entity with respect to phi. Okay. So, this is the assumption based on our understanding that the wavefront is going to be spherically symmetric. So, with that understanding, I am just going to write directly the equation which governs in a radial in a spherically symmetric system. I am not going to do the derivation, but if you are interested in derivation, I encourage you to look at some of the texts which have been referred. So, in the 1D Cartesian system, the 1D wave equation was, so it should not be 1D Cartesian system, it is Cartesian system, and this is the equation for 1D wave. So, this is equal to second derivative of pressure in with respect to time equals c square times second derivative pressure with respect to x. So, for a spherical system, a one dimensional wave can be represented by an equation which looks similar, but it is not entirely similar. So, in Cartesian frame we had just partial derivative of with respect to partial derivative of pressure, but here it is partial derivative of pressure times radius. So, this is the wave equation. So, second derivative of p times r in time equals c square equals c times second derivative of p times r with respect to r. And what is r? R is the distance of point P from the source. So, this is source and this is r. Okay. So, this is the governing equation for pressure. So, for 1D pressure wave. Similarly, the governing equation for one dimensional velocity wave is so in this particular course we are not going to develop the expression, but at this stage we will just write the equation, and if you are interested you can go and look at the derivation from some of the standard texts. So, this is the governing equation for 1D velocity wave, and this is in spherical coordinate system. Now, let us look at the solutions. So, we will just draw an analogy. So, for Cartesian system, the solution for P was f1 any function f1 which depended on t minus x over c, and that was a forward travelling wave. Okay. So, similarly, the structure of the equation is very similar. So, a solution for P and U, it can be written as P times R, because here this is the entity which is being differentiated upon, right. So, this is P times R equals f1 of t minus R over C. Okay. And similarly, for wave u times R is equal to f1 t minus R over C, or you can write it as P which depends on R and T is equal to f1 t minus R over C divided by R, and from here you get u which is a function of R and T is equal to f1 t minus R over C by R. Okay. So, this is the solution, and you can prove it to yourself that if you plug in this relation in these differential equations, you will see that the left hand side and the right hand side they satisfy, they become equal. So, these such functions, generic functions, they satisfy the differential equation. So, this function is, our guess for this function is correct. Now, because this is t minus R over C, it represents a wave which is travelling outwards. It represents a wave which is travelling away from the source, because origin is located at the source. If there was a reflected wave, I would have included an f2 where it would have been t plus R over C, but in this course we are not going to discuss, at least at this point of time, reflected spherical waves. So, this is a general solution, but if we have to express this solution in terms of exponent, in terms of complex variables, then we can write it as, so alternatively, if we have to express them in exponential formats, then we can write it as P of R t equals real of P plus E j omega t minus R by C divided by R. So, this is my complex pressure, and if I take its real component, I get the actual pressure. Okay. And I can also rearrange the term in the bracket as real of P plus R omega E minus e to the power of j omega t, where P plus is complex pressure amplitude at radius r, and that equals P plus by R times E minus j omega R over C. Okay. Similarly, velocity can be written as real of u plus over R E j omega t minus R over C. So, let us call this equation 1 and this as equation 2. So, now what we plan to do is, so this is the equation for pressure and this is the equation for velocity, and what we plan to do today is figure out how was u plus and p plus connected. So, that is our question, how are u plus and p plus, oops, p plus and u plus connected. Okay. So, in 1D Cartesian system, we had coupled the relation, we had found the relationship between p plus and u plus by using the momentum equation, which is essentially the statement of Newton's second law. So, we will use the same momentum equation, but as expressed in spherical system, and using that equivalence we will connect the equation for pressure and equation for velocity. So, that is what we plan to do in our next class, and that concludes our discussion for today on one dimensional spherical waves. So, thank you and have a great day.